everybody. And I'll do an official welcome. Okay, so we are going to look at the final exam. And everyone that's watching this on video has Raul to thank. If no one showed up, I wasn't going to record this. So actually, thank you for giving us a proper class. Here we go. I am going to just kind of scroll for right now. We'll talk about it. This was one of our first assignments and quizzes and questions in exam one of our first assignments from chapter 2. Remember, as you're doing this problem, I'm not even set up to do this. So on number 1, don't forget to use parentheses. If you choose to put this in a grapher or even just a regular calculator, make sure you use enough parentheses. So this is going to be our major form. How about I have to erase all of that because I forgot to give me more paper. I don't want to get to the end of this page and be done. All right, back up. There we go. So yeah, make sure when you're using it in the calculator in any way that you use enough parentheses to take care of this. And this problem will not be an issue. We know that this answer is going to be 5 because of that 5 in front. A nice little fact that makes this super easy at the end is that the limit as x approaches 0 of sine of x over x equals 1. So this 5 being in front, the 5 moves to the front, 5 times 1. This answer everybody should get because of this fact. These ones, it varies. 5 decimal places. So that's a lot to keep track of. Make sure you round appropriately. Also, Ro, feel free to pop in anytime you have a question or you want further explanation. For number 2, I would absolutely, let me tell you, 20 questions on the final. I think there's 25 or 30 on the review. Yeah, there's 30 on the review, but there's only 20 questions that are actually on the final exam. And we tried roughly for about 7 from each chapter, 7 from each chapter, 1 chapter, not each chapter, from each exam. Okay, but all of these questions you've seen on an exam before. Always evaluate first. Just plug it in. And if we get 0 over a number, that's cool. If we get a number over 0, we have to determine which infinity this is. If we get 0 over 0, we have to do work. And any other number, so just n over m is okay as well. All right, so he's not alone. So anybody that has questions, thank you for showing up. Just pop in with questions if you have them, when you have them. Okay, so we always try to evaluate first, and I can see we're going to get a 0 in the denominator, but it turns out that 25 plus 10 makes 35, so we're going to get 0 over 0, and we have to do work. This one's absolutely okay. It's equal to 0. A number over 0, that's one of the infinities. You have to determine positive or negative. If you get 0 over 0, do work. If you get any other number, it's all cool. All right, number 3. And remember, these are pooled, so it's just the number 3 that I'm looking at from my question. But they are going to be the same pooled questions. So whatever pool this was in exam 1, it's the same options probably that we're going to have in the final exam. most likely. I happen to know the coordinator of calculus this semester, and she's kind of lazy. You know her too. We had all semester together. Okay, so we want to just discuss the continuity, and continuity does depend on, you know, the domain. There's some interaction between continuity and the domain, and I noticed right away that x equals -1 is going to be an issue. Just because we're algebra experts, since we know calculus, it's going to be discontinuous where this hole is. Don't overthink these problems. You've been doing these for 4 months now. And I don't mean to say it this way, but this is the easy part. The hardest part is remembering it because it was so long ago. But don't overthink it. All right, number 4, some one-sided limits. Always the same as number 2. Same as number 2, we're looking for what type of output. If we get a number over 0, we need to pay close attention to the positive from the right and negative. Whoops, I'm going to use the negative sign from the left. That's the only difference. And because there's a cosecant involved, there's absolutely going to be an asymptote going on here, I think. Oh, there's not. Let's do number 4. It involves trig. It's one of those things where more people than not would really like to see it worked out. Something I'd like to point out, trig-wise, cosecant is 1 over sine of x, but more importantly, sine of x is 1 over cosecant. So what we're really trying to find here is the limit as x approaches pi from the right of the square root of x times the sine of x. All right, sine is 1 over cosecant. Now, cosecant is never 0. Cosecant is always bigger than 1 or smaller than -1, so I don't have to worry about any zeros, actually. This is pi times sine of pi, and I happen to know that the sine of pi is 0. This should be 0. And now, right, sine of pi is 0. It is indeed. But now I kind of want to check that. Now I'm starting to think, maybe I'm lying to you. Not on purpose, so it wouldn't be a total lie. Still a lie. Don't let anybody fool you on that. Okay, let's look. Square root of x. Pull up my keyboard. And we're going to divide that by, divide that by cosecant of x. If we look at pi, yep, we have a value of 0. So fantastic. It is exactly the value of square root of x times sine of x. You can see the sign in there, and we can see how kind of the square root adjusts it. It makes it a pretty cool wave overall. Notice how it's amplifying larger and larger and larger as we go along. This is kind of how sound waves travel, only they get further apart as well. All right, cool. I like that. I told you the right answer. That's what I like the most. All right, how are we doing? Class, good. All right, thank you very much for that feedback. Number 5. All right. Now, when I tell you, do not overthink, I mean, don't overthink this. When it comes to math, everybody has an easy time making it harder than it should be. Number 5, slope of a tangent line. And we know that this is the derivative at a point. But if we're given something like, oh, I don't know, a linear function, this is linear. It's always going to have a slope of 9/4. That's always going to be the derivative. It doesn't matter what the point is. Find the slope. The slope of a linear equation is 9/4. Thanks for the points. Move along. Don't make it out to be something hard. Don't look at it and say, nah, that's too easy. It can be easy, right? When you understand math, it really is that easy. Number 6. Differentiation. This will be some kind of trig, I'm sure. My example. Just derivatives in general. Don't forget your trig derivatives. I'm going to use horrible notation. No, I'll do it right. The derivative of sine is cosine. The derivative of tangent is secant squared. And the derivative of secant is secant x, tangent of x. Everything's pretty much the same for the cofunctions, but the cosine has derivative negative sine. Remember our wheel, it was on the board. It says sine, cosine, to negative sine, to negative cosine. That's our derivatives and our anti-derivatives. Go the opposite way. So derivatives take clockwise view, anti-derivatives go anti-opposite of the clock, so counterclockwise. Over here, the derivative of the cotangent. Tangent and secant go together in the Pythagorean identities. So cotangent and cosecant go together. And because it's cofunction, it's negative. The derivative of cosecant is negative cosecant cotangent. So if you know these 3, you can figure out the other 3 because they're negative. All the derivatives of cofunctions are negative, and they're very similar in how they interact. So don't overthink this one. This one has actually derivative. Pi over 3 is a constant. Derivative of sine is cosine. That's it. It's been a while, but exam 1 compared to what you guys are doing now really was straightforward. You can have several that are just find the derivative. So it looks like 6 through 8 is just use the rules of differentiation. And don't overthink. Second derivative, so we got some work on number 8, but just use substitution and all of that. Let's go ahead and use implicit derivatives example. Implicit differentiation always uses y as a function of x. So the derivative of y is dy dx. All right, and our example is the square root of xy equals x to the 4th y plus 44. I am cruising kind of fast. There are 30 problems here. Like I said, just holler out. I know neither of you are shy. It's okay. You can ask questions in class. You can ask questions here. So shout it out if you have it. Otherwise, I'm just kind of going blah with all the math. All right, so there's two ways I was thinking of doing this. And I think I want to approach it most like a student would. And I'm hoping at this point, I have used the square root as the 1/2 power enough that maybe that's your first thought. But I want to remind you, this is a power property of the product. If we have a product raised to a power, then we could raise each individual factor of that product to the power. So I could call this x to the 1/2 y to the 1/2 equals x to the 4th y plus 44. Now this little step avoids the chain rule. So algebra, super important, because algebra, little things in algebra make the calculus easier. Now I can just use a product rule. So we take first, derivative of the second, derivative of y to the 1/2. We think of y as something, right? So it's derivative of the outside, 1/2, y to the negative 1/2, times the derivative of the inside, and the derivative of the inside, y is the inside, so dy dx. So first derivative of second plus second times the derivative of the first, and then we keep going, product rule again. First derivative of second plus second derivative of the first, and finally we get an easy derivative. Derivative of 44 is 0. I'm going to simplify before I do anything else with this problem, because this is hideous. It always comes down to the algebra. So I have x to the 1/2, y to the negative 1/2. I'm going to call that 1/2 the square root of x over y, right? X in the numerator, y in the denominator, both have a square root, 1/2 times dy dx. Plus, now this is just the opposite. Now the y is in the numerator, the x is in the denominator. Equals x to the 4th dy dx plus 4yx cubed. So now I'm going to get all of these dy dx's on the same side, and anything without a dy dx, I'm going to take to the other. So we have 1/2 the square root of x over y minus x to the 4th that are all times dy dx. I've moved this one over and factored out the dy dx all at the same time. Here we'll have 4yx cubed minus, I don't think I like how I'm writing this, so I'm going to switch it up a little bit. Oh no, I don't want to switch it up a little bit. I see something nice that's going to happen here in our next step, so let's write it like I have the other one written. Minus the 1/2 square root of y over x. Moved it to the other side, so it's negative. To get dy dx by itself, I am going to be lazy. 4yx cubed minus 1/2 square root of y over x, all divided by 1/2 square root of x over y minus x to the 4th. I want to make sure that I end that radical before I put the subtraction though, so I know that it is not under the radical when I enter it into WebAssign, as I'm checking my answer or entering my final exam answer. And so it looks kind of nasty, but it doesn't say reduce here, so I'm going to go with it. I'm also not going to whisper when I record. All right, that's the first 9. Everybody's favorite problem is the trough. The trough problem. Let's go ahead and work through this one. A trough is 12 feet long, 3 feet across the top, and its ends are isosceles triangles. So I know that if this is 3 feet, I know that this angle is, it's nice. It's super nice. This actually, nope, is not what I was about to say. Isosceles triangles. So it's a nice angle here. We're good. We're good. We're good. And our water depth, so let's bring this back here. Our water depth, let's make it blue. And nice clean water. Has a depth of H. We're also pouring water into this thing. So it's coming in. Okay. I know that the rate of the flow is 2 cubic feet per minute. And if I think about what this really says, cubic feet is a volume per minute. So now we're looking at a rate of change, and we're changing with respect to time. So looking at the units alone, I know what this is going to be. I know I'm looking for a volume in this problem. So I'm looking for a volume of a trough of this particular shape. Let's see. If water is being pumped into the trough at 2 cubic feet per minute, how fast is water level rising? So find dH dt when H is 1.8 feet deep. And then I just had this minute of, oh no. But it's okay. Since this height is 3 and this width is 3, we happen to know that this length here is also H. Whatever the depth of the water is, it's also the length across the trough, just because of how the trough is set up. So let's look at an end. This end is 3. This height is 3, which means if we put a height right here, I could pull this out and look at a triangle if I wanted to, but I probably don't want to. What I want to do instead is silence my phone. My area is 1/2 base times height. Now our height is adjustable. Our height varies. Our height is actually 3/2 H, right? Because the base is 3 and the height varies because we're adding water. That base is always going to be 3 of the whole. Ooh, that's not true. The water will have a base equal to H. That's what I just said right here. Whatever height the water is, that's the width. So wherever we happen to be at our height of H, it's not going to be 3/2 H. It's going to be 1/2 H squared. I think that's where I messed this problem up on our first attempt. And now the volume of any 3-dimensional object will take the area of an end times the length. So this is a 1/2 H squared times 12. That 12 will be consistent throughout the entire problem. It's exactly 12 feet long. So our volume is 6H squared cubic feet. We know dV dt is 12h dH dt. And now we can fill in our values. Let's go back to purple. 2. No. Come on. Sorry for the jump there. I was evidently talking too fast. Even Word didn't like it. So we have 2 equals 12 times 1.8 dH dt. I want to find dH dt. 12 times 1.8, 12 times 1 is 12. 12 times 8 feels like 96. Yep. So 12 plus 9.6, because it was a decimal, is 21.6. Yes, I'm going to check that on a calculator. In class, I just look up and see who had it already, but I'll do it for you. Oh yeah, no Alzheimer's for me today. I'm going to keep my math sharp. 2 divided by 21.6. Ooh, that's pretty tiny, isn't it? 0.09259 dH dt. I'm afraid this is wrong. I'm going to tell you right now. What do we want? We want 3 decimal places. Nope, we don't want 3 decimal places. Uh, 0.0926. I don't like it. I'll take it though. You see that? I got lucky. Good. I learned something this semester too. I learned that I can remember how to do a problem that we've done before. If the water is rising at a rate of 3/8 inches per minute, oh, I remember Jennifer had to help me on this one. The second part of the problem, let's throw it down in dark blue. If the water is rising at a rate of a 3/8, so the height is 3/8 of an inch per minute when h is 2.4, determine the rate at which the water is being pumped into the trough. However, keep an eye on the units here. We want to find dV dt in cubic feet per minute. So inches versus feet. And we're going to use this same formula both times, but the first thing I'm going to do is convert this. 3/8 inches. We will have 12 inches in 1 foot. 3 and 12 simplify to give me a 4 in the denominator. This is 1/24 of a foot. This is inches per minute. All right, so 1/24 of a foot per minute, 3 inches. So now when we substitute into our formula, we want to find dV dt when h is 2.4 and dH dt is 1/24, and all of our units work out. This is feet, this is feet, and our 12 as that happens to actually be feet as well. Let's see. It's 24 and 12. I have a 2 in the denominator. That's feeling like a 1.2. I encourage you to check my calculations, but I like living on the edge here. I got it wrong. How did I get it wrong? I probably should have used a calculator. I don't know. I'm pretty sure that's 1.2. Divided by 24. All right, so I did something wrong in here. I know what I did. Right here. Check it out. 3 goes into 12 4 times, and 8 times 4 is not 24, it's 32. And so instead of dividing by 24, how about we do it correctly and divide by 32? And we'll get 0.9. And then we'll try that answer when we do the arithmetic correctly. See, I should never be allowed to attempt things without a calculator some days. All right, I got one, but not the other. Oh yeah, I'm good, I'm good. How can I do that in my head, but not do that? Seriously, don't overthink this, people. All right, how are we doing on the trough problem? Related rates, good stuff. Fantastic, all right. I'm going to scroll through some others. We'll just kind of go back to this looking at it quickly idea. The problems that I think more people have issues with, we'll go over those too. Absolute extrema. Remember absolute extrema on a closed interval? We want to check critical numbers. And that's when the derivative is 0 or does not exist. And endpoints. The biggest y is the max, and the smallest y is the minimum. And remember, we always go minimum. Always go back to the original function to find those y values. So go back to the original to find y value. The derivative tells us where. Which values to use. How about that? But the original is the what y is. All right, so the derivative will tell us where to look, but we always look at the original function in order to make it happen. All right, so absolute extrema, you guys could totally do that. Remember the Rolle's theorem? Rolle's theorem we'll check is continuous on a closed interval, A to B. It has to be differentiable. So derivative has to exist on the open interval. And it must be that f of A is equal to f of B. Then, so these are all if. So we check those three things. Then what happens is there is some C so that f of C is equal to 0, C in the interval. There we go. Then there is some C in the interval from A to B so that f of C is equal to 0. Now the mean value theorem is very similar, but slightly different. And they're in the same section. So we still have to check if f is continuous on a closed interval and f is differentiable on the open interval. And remember, that just means the derivative exists everywhere except for maybe at the endpoints. And that's all that's not all we need. We need mean value theorem. Which one am I trying to think of here? It's continuous and differentiable. I think we go straight to then. There exists C in the interval from A to B. This little E, this funky looking E, means element of, so it's in that interval, such that f of C is equal to the slope of the line through the endpoints. So really, if f of A equals f of B, right, we'll get a 0 up here. So Rolle's theorem is a special case of the mean value theorem. The mean value theorem always works, no matter what. But if it just so happens that the endpoints are the same value, then we call it Rolle's theorem. And Rolle thought it was important enough that we have it. So way to go, Rolle. And I think I probably should learn who he is since I teach history and math. All right. And then find that time t, that's that C value that it's looking for. Critical numbers, first derivative test, all of this. Let's look at 13, 14 together. 13 and 14. Closing up on, we're only halfway through this review. I'm so sorry. Maybe I should scroll some more, but I'm trying, my dogs are about to go off. I'm trying to get through the things that we haven't talked about for a while. Remember that our first derivative has critical numbers, right? First derivative equal to 0 or does not exist, has critical numbers. And then we'll use the test points to find the plus or minus sign of the derivative on intervals. If we have an interval where we go from increasing to decreasing, we'll have a maximum. If we have an interval where we go from decreasing to increasing, not an interval, two different intervals, critical number where this happens, we'll have a minimum. This is our first derivative test. Changing signs, really what we're looking for. The second derivative has points of inflection. And we'll use test points. Test points to find the plus or minus sign of the second derivative. And we'll have things like if it's positive and then negative, it's concave down. If we go from negative to positive in sign, it's up like a cup, concave up. And so these are very, very similar, right? We haven't seen them for a while. All right, put your seatbelts on, here we go. You can evaluate limits. For limits, we could really just look at the leading terms. Although if we're looking at a limit as x approaches infinity with a square root involved, remember that x squared is, in this case, the sign might be different. The square root of x to the fourth. Actually, the sign won't be different in this case. These are equal. We might have x. This one depends on sine with x squared. So when you're dividing by the highest power, make sure you take into account the square root action on it. Number 16 uses all the good stuff from 13, 14, and 15. This one's in the notes. Take a look at it. It's in, we want to maximize, it's in exam 2. So the table and lighting is in exam 2. Oh no, we've ran out of paper. That's all right. We've ran out of time too. In 18, we hit the, remember, if we have a differential equation, we find the antiderivative to find the original. This f of 0 is going to help us find our constant. And boom, here we are in exam 3 stuff, upper and lower sums that we've done for a while. As we're looking at our integral here, what is the region? Is from -3 to +3. What's our function? Our function is given to us right here. Fingers crossed. All right, I just have to fix one part of it. You know what it means to find an area under the graph of a function above the x-axis between the two values. You know how to fill this in. Not all of these problems are going to be a lot of time given to them. You could do this stuff in your sleep. Like seriously, your exam 3 is tomorrow. All of this at the bottom, we've got through everything from exams 1 and 2. I'm going to jump real quick. Oh, I don't have any more paper. Oh, that's a bummer. Did I leave any areas blank? I did not leave any areas blank, so I guess that's going to be it. I was going to do this one real quick. Don't forget about this sheet. I posted it on Blackboard in the week 15 folder so that you have access. And remember, as you're looking at some of these integrals, when I look at this, I think to myself, all right, a square root of something more than just x or u or whatever in the denominator. If I try to let u be everything under the radical for like a substitution rule back in chapter 3, I don't have any x's up here to deal with. So that's not going to work out for me. I think we talked about something similar to this yesterday's review of exam 3. So instead, I see a square root in the denominator. This part is square. I'm subtracting. This part is square. Seems pretty reasonable. It's going to be an arc sine formula. Not hyperbolic. Arc sine, right? The square root of 1 minus u squared. If we do it in terms of antiderivatives, here we are. The antiderivative of du over a squared minus u squared. So we have that form there. And if you try a basic substitution first and it doesn't work out for you, come to this formula sheet and think about the different formats that we could do. Yeah, and that's class done. Thank you both for being here. Do you have any kind of quick questions for me, or are you doing okay? All right, fantastic. Thank you for coming today. I really was just going to blow it off if nobody showed up. So you're the true heroes of this class. Everybody got a review because of you. Thank you. It's been a pleasure. I look forward to seeing your fantastic grades. I look forward to seeing you in the spring. Feel free to say, hey, when you're on campus, unless you hated class, then whatever, you can ignore me. I don't care. But I'll always have a smile regardless, even though you won't be able to see it. All right. Happy trails. Best of luck on your exam tomorrow. Exam 3 is tomorrow. Final exam, 2 hours, 45 minutes. Sometime Monday, Tuesday, or Wednesday. Your choice. It'll be open for that whole window of time. Thanks again, and I'll see you guys later.